All right, y'all. Good evening. Welcome. We are in our fourth week, finishing it up. So there's the main points from the last kind of class. I'll talk through those in a second. Just a reminder of what we did. But what I want to point out again, always some logistic stuff. So one, I posted just a reminder to y'all. If you go to the Files tab of our course, each week, usually Tuesday, ideally is when I'm doing it, or maybe Wednesday, I posted the solutions for the last quiz, the quiz that was due last Saturday. So if you open that up, it'll show you how to solve them. So if there's any questions you had questions about, check that out. So this week's quiz is on electric potential, so voltage and electric potential energy, due this Saturday. Just a reminder, 2 weeks from today is our test. 2 weeks from today, so February 15th. Thursday, February 15th is our test. I sent out an announcement detailing kind of how it's going to, I talked about last class, an announcement that in details. Today I was actually working on the test. I believe I've kind of got it polished down to what I want. I told you I was going to be 20 multiple choice. I think I've landed on 22 or 23. I forget the exact number. The more questions I honestly wish I could ask even more questions, not because I want to make your life more miserable, but because one of the things that when you're designing a multiple choice test, remember the questions are all or nothing. You either get the points for it or you don't. So the more questions I ask, the less consequence it is if you make a silly mistake and miss one. Because each question is then worth less points. But the more questions I ask, the more time it takes you to solve it. So there's this delicate balancing act that I have to kind of reach where I'm like asking enough questions so that if you miss one, it doesn't kill your grade, but not so many questions that you don't have time to go through them, take your time, check your work, all that stuff. So 22 is where I'm at now. I'll play around with it. The way I kind of figure out if that's reasonable is I will go through those questions, I will solve them myself. And then I'll take the time it takes me and multiply it by like 4. And that'll give me a sense of kind of like on the 3 or 4 is how much time I may expect you all to take. And when I'm solving them, I'm writing things out. Because writing things out, I want you to write things out. That takes time. And so there's that. But everything else should be basically what I sent you on the announcement. So again, instead of 20 multiple choice, it'll be 22 or 23. It'll still be only one free response. So, well, there'll be 2 choices. 2 free response questions, you pick one. So, whichever one you feel more comfortable with. If you solve both of them, I've met with the grader today, and this will be written on your all's thing as well. If you solve both of them, they're only going to grade the one that you check. However, they will quickly look at the other one. If you did the other one perfectly, they'll just give you the points for the one you did perfectly. Only if you did it perfectly. Again, to spare them having to grade twice as many questions. And to make it equitable and all that kind of jazz. So, if you do have the time and you solve both of them, and the one that you picked, you made a small mistake somewhere or, bigger mistake, but the second one you did perfectly, they will just quickly look, oh, you did that one perfectly, great, and they'll just give you all the points there. So, test is this day. Next week, I will have those 5x8 note cards for you all. So I will bring those here. If you want one, you can grab one. Remember, you all get to bring a 5x8 note card with whatever you want on the front and the back of it. That is in addition to the formula sheet I give you. So the formula sheet I posted, so you can see what formulas I give. Whatever you want to put on the note card, put on the note card. If there's something you think you'll forget, put it on the note card. Unit conversions, those are not on the formula sheet. If you're afraid you'll forget them, put them on the note card. If you want to draw pictures to show what things look like in the direction that electric fields point away from positive and towards negative, put that on the note card, either in picture form and word form or both. Whatever may be useful for you. Reminder on the formula sheet. So like one of the things that could be useful, there is 1, 2, 3, 4, 5, I guess technically 6 equations for electric field, because they're all for different, this one's the electric field due to a point charge. This one relates electric field force and that. This is electric field due to a sphere. This is electric field due to a line of charge. This is electric field due to a plane of charge. So that could be something you also put on your note card if you're like, oh, I forget which one's which. You can label those up. Just know this is what you're going to get in the formula sheet. So again, all sorts of options. Put whatever you want on there. It's yours. Just don't make it a flip book of a bunch of pages stapled to it. That won't fly. And if you forget your note card, you'll at least have the formula sheet. That's the reason I provide the formula sheet. In the past, people are like, oh crap, I forgot my note card at home. I don't want you to try to take it without the equations. So you have this, everyone has this. Okay. Last thing I want to point out to you all. So the test is this Thursday, is 2 weeks from today. Next week, we are going to finish covering a little bit of circuit stuff. Like every week, the quiz for next week will actually not be due to the 17th, which is after the test. Now, my recommendation to you all, sure, you can do the quiz after the test. I highly, 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 highly recommend you do the quiz before the test, because the quiz is worth less points, and it's better for you to realize before the test that you may not understand something, versus taking the test, realize you don't understand it, learning it, and then doing better on the quiz, which is worth less points. So the quizzes are there to help you understand what you know. So even though the quiz is due after the test, just like every other, due on that Saturday, please at least do one of the attempts beforehand so you get a sense of what kind of questions, what kind of topics, that kind of thing may be expected. But it's ultimately up to you. But that's my strong encouragement to you all. That also means that when we're going through the stuff next week, you clearly you kind of have less time than usual to kind of review that stuff. So you're going to want to start that stuff a little bit sooner. That's just how the timing works. There's not really any way around that. Outside of the only way I'd be able to get around that is to start to teach new stuff next week that would be on the next test, and then people are confused about which stuff is on the test, and then that just opens up a whole nother can of worms. So I avoid that. It's not ideal, and that you get a little bit less time for next week's content to learn it. But honestly, the stuff's not too bad. So that's kind of fortunate. Anyway, so that's that. So today, any questions about the test or any of that jazz? All right. Again, if you have questions at any point, shoot me an email. All right. So last class, we talked about capacitors. So capacitors, we basically kind of took so we took an infinite plane, and we said, hey, infinite plane, what's the electric field due to that? And it was sigma over 2 epsilon naught. We then said, hey, if we put two of them with opposite charge, what's the electric field due to that? And it's sigma over epsilon naught, and we said, hey, that's a capacitor. So these capacitors are basically just two planes. It's kind of it's got a bunch of drawing on it. Two planes with opposite charge, and they just store a bunch of charge. So these two planes store a bunch of charge. The electric field between them is sigma over epsilon naught, has no dependence upon distance. It doesn't matter where you are between them. Doesn't matter where you are, because they're infinite planes. It doesn't matter how far away you get from an infinite plane, the electric field is the same. So it does not depend upon distance, very important. The voltage does depend upon distance. If you make them twice as far, we asked a question about that. And as distance goes up, the voltage goes up because the electric field doesn't change. And then, we said, okay, what's the point of these things? They store charge. You can almost think of these like a bucket for water. So if you think of like a hose as like a wire, a bucket, you can fill up a bunch of water in that bucket, and I could dump that bucket really quickly and get a lot of charge out. A lot of water out very quickly. So these things store charge. There's a cue. So capacitance, capacity, kind of sounds like a similar word. That's where that comes from. The more voltage you put, the more charge we can get on it. So that's kind of what this definition says, is a charge per voltage. So if I hook up a really big battery to it, I can shove more charge on it. In fact, if you put too much voltage on a capacitor, it'll blow up. Because you get so much charge and no longer wants to stay separated, and the electricity bridges the gap and blows up your capacitor. And then this last one, this energy, we'll talk about that today. We'll do a couple problems with this stuff. And then we'll get into resistance. We'll probably finish the stuff for this week a little early, and so then I'll just start next week's stuff. And the result is, the more we get done, if, by next Thursday I finished everything, we'll just start kind of reviewing the things that are kind of more, that I traditionally know are tricky. Vectors. Shocking, right? And just electric field vectors, and that's what we're going to do. So next Thursday, if we finish early, we'll start that. But definitely the Tuesday before the exam, we'll also do some review problems. I'll tell you all that Tuesday before the exam. I'm not going to ask any clicker questions, at least none worth any points. I may ask some, but they will not count towards your grade. That's just a review day. If you think it's more useful to be here, be here. If you think it's more useful to study on your own, study on your own. But during the Tuesday before the exam, that'll be a review day where I kind of outline, hey, here are some things to keep track of. Here are some of the most common mistakes students make. I've mentioned a lot of these throughout the class, but it'll be kind of, I'll make a list of things. I'll say, hey, maybe here's some handy things to have in your formula sheet, in your note card, all that kind of jazz. So, anyhow. So we finished early today. That just means we start the next stuff early, and then that'll give us more time. So, all right, great. This last thing, energy stored in a capacitor. I started to talk about that last class, but it was right near the end. So the energy a point charge has is Q times V. The energy a capacitor has is 1/2 Q times V. And literally the only difference between these is a half. So if I ask you for the energy stored in a capacitor, and I give you charge, and I give you voltage, and you use this equation up top, you will get the wrong answer. So, again, let's kind of look at that formula sheet. That's one of those so energy equals Q times V. Let's see, am I missing that other one? Oh, I am. Okay, so that I remember there was one I did. So I'll add the one for the energy capacity. Oh, there it is. Nope, it's right there. U equals 1/2 QV. These look almost the same. They both say U equals Q times V. One's got a little q, one's got a big Q. Again, this is one of those, you have to know that this is for a point charge, the one that's just QV. You have to know that that's the one for a capacitor. Just like when we talked about electric fields. This is the electric field due to a point charge. This is the electric field due to a plane of charge. So again, those won't be clear. They're not labeled any different. You'll have to kind of know that or write it on your formula sheet. So, the equation for the energy in a capacitor is 1/2 Q times V. That comes from doing an integral, which is why I'm not going to show you where it comes from, because the majority of you have not had to do calculus. What a shame. I know you're very sad about that. The majority of you have not had to do calculus, so I'm not going to do the derivation because it won't benefit most of you. And we'll just even say capacitor there. But it's 1/2 Q times V. Now, how do we get these other equations? So we remember that C equals Q over V. So that's the definition of capacitance. If I just rearrange this equation and I say Q equals CV, all I did is rearrange it. And if I plug that right there, so the energy stored in a capacitor is 1/2 Q times V. Just replace the Q with CV. And ta-da! We got the second equation. That's all it came from. It's not like a new one. It's just it's replacing one of the variables using a different relationship. So that's where the second one came from. Okay. If I want to get the third one, okay, I'm going to take this, and instead of solving for Q, let's solve for the voltage. So voltage, if you do the algebra, will be Q divided by C. Same thing. Just plug that in right there. And we will find that U capacitor equals 1/2 QV equals 1/2. Just replace the V with Q over C. And we get 1/2 Q squared divided by C, which is that one. That's all I did. Very simple kind of plugins. Again, on your all's formula sheet, I only give you this one. So if you want the other ones, either just know how to do the algebra or write it down on your 5x8. The choice is yours. But how to get that is just from these substitutions. Okay? So depending on, why is there 3 different versions? What's the use of this? If I say find the energy in a capacitor and I give you charge and capacitance, use the last one. If I say find the energy in a capacitor and I give you capacitance and voltage, use the second one. If I give you energy and capacitance and I say I give you charge and voltage. Sorry, this was capacitance voltage. And I give you charge and voltage, use the first one. So capacitance and voltage, second one. Pick whichever one, or alternatively, you can use C equals Q over V, find the one you're missing, plug it in, and do the things. So many options. As with most of these things, if you're like, what the heck? You just said a bunch of words. When you all start solving problems with this, it'll make sense. This is fairly simple math here, and once you just do a couple problems, it won't be bad. All right. So now, what we're going to talk about, I have three variables here. I have charge, voltage, and capacitance. And so we're going to investigate what it would take for these three things to change. So we're going to do a few clicker questions, and these ones are going to be a little, tricky. If you know the definition of capacitance, if you know the definition of charge, and you know where the thing gets voltage, these are good problems. These help us to understand how a capacitor kind of works. Class, don't even know how this makes sense. Will it work? Will it make me log in even though it's already open? Good news, I've memorized my password so I don't have to look it up and risk showing it to everyone again. Alright, you all can see the question while this decides what it wants to do. What stays constant if I charge a capacitor with a battery, disconnect it from the battery, and then double the distance between the plates? So you can think about this while I determine why the iClicker app is so angry. What stays constant if I charge a capacitor with a battery, I disconnect it from the battery, and then I take that distance and I double it in the plates? Fun fact, we've already answered this question. All right, so hopefully you all have had a lot of time to think about this. So I'll give you 30 seconds. Won't wait that long. Just give you all enough time to respond. So what stays constant if I charge a capacitor disconnected, double the distance? Is it charge, voltage, or capacitance? All right, and we'll close it out in 5, 4, 3, 2, 1. Okay, so the key to this one, we've already talked about this. Voltage in a capacitor, this is kind of a throwback to something we did. V equals ED. Again, this problem is the same as, is it this one? Nope, that's the electric field. That one, nope, not that one. There it is. I got some, again, it's this problem, just to look different. This capacitor was charged, but the result is the same. The voltage in a capacitor equals E times D. The electric field in a capacitor only depends upon the charge. My thing's charged, the charge doesn't change. If I take these plates and they got a bunch of charge on them, they're separated. This one's got a bunch of positives. This one's got a bunch of negatives. If I double the distance between them, well, that one's still got a bunch of positives. That one's still got a bunch of negatives. The electric field is a constant. If the distance doubles, then my voltage doubles. The right side got doubled. So the voltage doubles. Okay? Oh, sorry. That's okay. My apologies here. That doesn't make sense based on this question. This question's not saying what changes. This is saying what stays the same. All right, so one of them, we just said the voltage changes. Great, we know that changes. We're going to actually, there's a few ways you can do this. Let's look at the equation for capacitance. And I've kind of already given you all the answer for what stays the same, what changes. Fantastic. Everything's weird. All right. The capacitance is epsilon naught A over D. That's the equation for capacitance. So C equals epsilon naught A over D. So if the distance doubles, the capacitance is going to change. And let's see if it does the thing I'm so afraid of it doing. Ah, it didn't. Fantastic. All right, so great. The capacitance is going to half. So that changes. All right, great. So honestly, figuring out what changes was the hard thing. Here's the easier way to think about this one. If I charge a capacitor and I separate these plates, the charge stays the same. Why? If I put charge on there and I move the plates apart, if it's separated from the circuit, it can't go anywhere. Again, it's literally like I filled a bunch of buckets. I filled 2 buckets. Well, because it's 2 plates or whatever, and I just move the buckets apart from each other. The water in the buckets is the same. Me moving the plates doesn't change the charge on them. I could take these 2 plates, I could rip this, if I could somehow rip this capacitor in half and ship one half all the way to China and keep the other one here, they would still have the same amount of charge. Charge cannot leave it unless it has somewhere to go. If you put a bunch of charge in there, it's going to stay there until you discharge it. So the charge is going to stay the same here. Voltage will change, we showed that. Capacitance will change, we saw that. But the charge will stay the same. Alright, so that's what stays the same if I double the distance. If I disconnect it from the battery, that was very important. What stays constant if I charge a capacitor, I leave it connected to the battery, and then double the distance? What's going to stay constant if I charge a capacitor, leave it connected to a battery, and then double the distance? So the difference between these, the last one was disconnected from the circuit, meaning they were isolated. This one, they're still connected to the circuit. So if I draw a picture of this, I've got a battery, and I've got one plane here, one plane here. So that's my original situation. The new situation is I double that distance between them, but it is connected to the same battery. My original distance was D. My new distance is 2D. These are fun little questions. They just help us kind of understand what's going on in a battery. They're weird, but they are useful. They help us understand how these variables, what they are, how they relate. We'll go to 120, so 15 more seconds. There's five, 4, 3, 2, 1. Okay. So again, there's 2 angles we could go here. 2 angles we could go here. We can either figure out what things change and then process of elimination, figure out what stays the same. Or we can just kind of start with what stays the same. I'll go through all of them. So this one is kind of a recap of the last thing I taught you all last class. And that is, why do these things? Will a capacitor charge? What even charges a capacitor? Why does it get charged in the first place? It is the battery. The battery charges the capacitor. So we said we put this battery there, and when you put this battery there, there's a voltage, and this voltage makes the charges say, oh, there's a higher energy here, lower energy here. They move to lower energy. In the case of electrons, that means they move to a higher voltage, lower energy, higher voltage. Remember, potential energy, different things. But this will not charge forever. The capacitor will stop charging when it receives the voltage of the battery. When basically the voltage at the positive end is the same as the voltage on the positive end of the battery. When the voltage on the negative end is the same as the voltage on the negative end of the battery. That's when it stops charging. When there's no longer a height difference. It is no longer more favorable to go to the battery, or on the bottom case, to go away from the battery. So long story short, if you just have a capacitor hooked up to a battery, it does not matter what that capacitor is. You could have a million different capacitors and hook each one up to a battery. They will all eventually have the voltage of the battery, regardless of what kind of capacitor it is, regardless if it has a bigger distance, bigger anything like that, because a capacitor will always charge to the voltage of the battery as long as it stays connected to that. Now, again, we could look at, okay, what about the other 2? Okay, voltage stays the same. We said all that. But show me why capacitance changes. So capacitance, this is your equation. This is the only, like, when it comes to capacitance, capacitance is purely dependent upon geometry. Like, and I say geometry not in a math sense. I say geometry in the sense of literally how the capacitor is made. How big is the area on the plates? What is the distance? That is fundamentally, it's kind of like a bucket. What determines whether a bucket can store a lot of water? You know, the height of that bucket and the area of the bucket, and you can do some and figure out the volume. It's kind of almost like, it's not a volume, but that's kind of the logic here. Same way, what determines how much water a bucket can store? How big the bucket is. What determines how much charge a capacitor can store? The area of it and how close the plates are. So if you change the area or you change the distance, you change the capacitance. Guaranteed. Guaranteed. If you are changing the area or changing the distance, you are changing the capacitance, regardless of anything else that happens. So you can see there, great, if I double the distance, it does not matter whether or not it's hooked up to the battery. It's half the capacitance. All right, so capacitance is pretty easy to explain. What about charge? Charge is a little trickier, but the key to remembering charge is remembering something else we talked about. The electric field stays the same as well. Remember the electric field and the the electric field in the capacitor stays the same. So the beginning electric field is the same as the ending electric field. Remember, it doesn't matter what happens to distance in a capacitor as far as the electric field. No, that's a little messy. So let's see here. We're going to actually use V equals ED. Let me process this a bit. The electric, I was lying to y'all. The electric field does change. The electric field does change, and therefore the charge is changing. Why is the electric field changing? Again, it's kind of circular logic. It's going to get more charge on it. So unfortunately, proving why the charge stays the same kind of relies on you knowing the voltage is going to stay the same, and there's not really any way to prove that independent from that fact. So there's no real point to me. Unfortunately, for you to understand that the charge changes, you have to know voltage stays the same. So there's not really... I can't do those separately, unfortunately. So what do you take away from this? I said a bunch of things. If you're hooked up to a battery, you get its voltage, regardless of what capacitor it is. If it's the only thing in the circuit, it gets its voltage. That's what to take away. Last one, what's the takeaway? Charge. Once you charge something, as long as you don't discharge it, it keeps it. And the last one, go ahead and tell you process of elimination. You can probably guess what the last one's going to be. If I charge a capacitor, disconnect it, use it to light up a light bulb, and then I chuck it across the room, ship it to China, who cares when I take it to the moon? What's going to stay the same? So I take it, it's no longer connected to the battery. I have discharged it by connecting it to a light bulb and lighting up that light bulb. All right, we'll go to 55 seconds on this one. In 5, 4, 3, 2, 1. All right, so what stays the same here? If I do not change the area and I do not change the distance, the capacitance stays the same. If I do not change what my capacitor looks like, I don't take it apart and fiddle with it. It doesn't matter if you charge it, discharge it, all those things. Easy example of this. If I buy a capacitor, it's kind of like buying something. If I buy it from the store and it says, so something I don't know if I've mentioned to you all, and I probably haven't done. The units for capacitor is farads. I don't know if that, I may have shown that before, but I don't know if I emphasized that. Units for capacitor are farads, so I'll mention it now. Units for C are farads, named after a guy whose last name was Farad. Anyway, if I buy a 3 millifarad capacitor from China and it arrives here, it better still be a 3 millifarad capacitor. Like, regardless of what happened to it. You know, if I use it in a device, it still better be the same value. Otherwise, it would mess up a bunch of circuitry. As long as, so C equals epsilon naught A over D, as long as I don't change the area and the distance, it stays the same. That's what it's based on. Okay. So a bunch of kind of things around here. These are good questions to kind of go back and look at and think about. It may seem confusing right now. It may seem like, what's the point of this? The point of this is it's going to help you better understand voltage with regards to circuits. So that's what we're going to be spending the next week on. That's what we're going to be spending after the first test. We're going to do more stuff with circuits. And so it is going to be very important for you to understand what voltage is. So that came into the last one. For this test, it's very important for you to understand capacitance is how much charge is stored, and it's based on this. That's very important. And then the first one, it's important for you to know that, again, what does a capacitor do? It stores charge. As long as you don't discharge it, it still has it. So there you go. All right, there's the old main points from last year. I got a couple slides farther. I don't think there's anything. Yeah, there's a couple of new things here, so I'll leave it here, but it says everything I just said. So feel free to look at that. Okay, there's one last little things we can do with capacitor to change it. This is not a huge deal. You will see like a question with this, but it's very simple. It's the last thing I'll mention. So we've been playing around with this capacitor equation. We said we could change the area. We said we can change the distance. There's one last thing we can change. We can put something between it. We call this a dielectric. So everyone we've done up to this point had literally nothing, a vacuum between it. In the real world, it's very hard to make a vacuum, and actually it's not even as good as putting a piece of plastic between it. So this dielectric is an insulator. It's an insulator, meaning charge does not conduct. That's very, very important, because if this was a metal, if I put a metal between the capacitor plates, the charge is just going to go across it, and then it's not storing anything. So it has to be an insulator. It has to be something charge cannot flow through. Now what that does is this actually is a good reminder from way back in the beginning where we said, what happens if we put an insulator near an electric field, near some charges? What will happen, so this insulator, when we put it here, has charges in it, and it makes dipoles. It moves, so every single one of these atoms, the electrons get pushed a little bit to the left. Every single one of the atoms, the electrons get pushed a little bit to the left, and we get these dipoles everywhere in it, and the net result is that I get this separation. Again, this is kind of a throwback to remind you all what I'm referring to. This is with the whole, why does a balloon stick to a wall? If you charge a balloon with negative charge, it will push away the negatives. Positives will be here. Okay, so same idea. Again, throwback from the first week. Okay, why is this useful? Why is this useful? By separating these charges, so the electric field of the capacitor points left to right. But if we look at the electric field due to the dielectric inside, it points the other way. Remember, electric fields add, so that will actually make this red one a little bit smaller. And what does that mean? That means I can actually put more charge on it. It's easier to add charge to it. I mean, another way to think about it, these positive charges here are basically going to let us attract more charges here. These positive charge, these negative ones here are going to push away. So long story short, all those words I just said, what's a takeaway? If I put a dielectric, I increase the capacitance. That's a takeaway. Now, sure, again, this talks about why. I'm going to kind of fast forward a little bit through this. Here's what you need to take away from this. After all those things I said, all those, why does it help? What is this dielectric? All you need to know is that if you have a dielectric in something, aka you put something in between a capacitor, it's an insulator. Remember our original equation for capacitance was epsilon naught A over D? If you put a dielectric in something, now it's kappa, that's the dielectric constant, A over D. Literally, it just take your dielectric constant for whatever material. Paper, it's 3.7. Mylar, just a kind of plastic, 3.1. Pyrex glass, pure water, look at that, it's 80. Strontium titanate, some weird chemical material, I don't know. If you put pure water, fun fact, is an insulator. The only reason water conducts electricity is because it dissolves a bunch of ions in it. Your blood is very conductive because it's got a bunch of minerals in it. We'll talk about that eventually. But if you put pure water, not with a bunch of crap in it, deionized water, it makes your capacitance 80 times larger. If I put a piece of paper between my capacitor, between those plates, it makes it 3.7 times larger. So it's very simple math. Take your normal area, take your normal equation, and just multiply it by the dielectric constant. You will not have to calculate the dielectric constant is not something you can really find. How do you determine this? Experiments. These dielectric constants are determined by experiments because it's incredibly, it really comes down to how easy is it to make a dipole in that thing. Water, really, I mean, there are already dipoles on there. It's really easy to kind of just orient all those water molecules to make a, polarize them strong. And then the other materials, same thing. Okay? So that's all you all need to know here. This right here. If I put a piece of plastic, if I put an insulator, if I put a material between my plates, I get a stronger capacitor. Which is also convenient because how do you make a capacitor? Literally, like, you all can make one at home. Just get some aluminum foil, put a piece of paper, then put another piece of aluminum foil on top, make certain your aluminum foil is not touching, you made a capacitor. If you want, roll it up. As long as the aluminum doesn't touch itself, you're good to go. That's all a capacitor is two conductors separated by an insulator. That insulator boosts the capacitance. So it actually helps. So that's real nice. And yeah, you can find these capacitors in all sorts of things. You break them apart, they'll just be a cylinder rolled up like that. Yeah?
So the equation is the dielectric constant is equal to, so what's CO?
CO is my original capacitance. Yeah. So basically, take a capacitor without that material. That's its CO. So this over here on the left. If I put something in it, just multiply by that. So for example, if I have a capacitor with nothing between it, absolutely nothing, this is kind of two plates, it will have a capacitance of C equals epsilon naught A over D. If I put pure water between it, so here was nothing, here was that. This one, my new capacitance will be 80 times my original. Because the water, the dielectric constant was 80. Yeah. Alright. And again, that's as far as we're going to go with this whole dielectric constant thing. Okay. So let's solve some problems with capacitors. So remember, capacitors are used when you need a lot of charge at once. So defibrillator is what I mentioned. The way a defibrillator works, you build up a bunch of charge, and then you complete the circuit using a human body as the completing the circuit. Then the electricity goes from one defibrillator to the other, passes through the heart on the way, and ideally that kickstarts the heart. But you need a lot of charge. Your skin is an insulator, so to run electricity through your body, you need a lot of charge, a lot of voltage. So you charge up this capacitor with a lot of charge, a lot of voltage, and you do that. Boom, there you go. Anyway, but it doesn't require much energy. It just requires a lot of charge. So what voltage is applied to the 5 microfarad capacitor of a heart defibrillator that stores 36 joules of energy? Find the amount of charge stored. There's not really a picture here. Again, pictures really come in when we talk about vectors, when we talk about multiple point charges and distances. I mean, I guess there's a capacitor. There's not every problem a picture is useful. So, what do we got? We got, actually, take 10 seconds to see if you can figure out what we got. Five microfarad capacitor stores 36 joules of energy. What are my givens and what variable do they go with? I mean, we know we have that, 5 microfarads. We know we have 36 joules. Really, the question is what variables do those go with? So, joules is energy. Always. Now, we have to know what type of energy. This is potential energy. The only other type we've talked about is kinetic. This is definitely not kinetic. And farads is capacitance. Farads is capacitance. Okay. And then first step done. Second step, spend 5 seconds. See if you can figure out what we're solving for. says, what voltage? Step 3, give you all a bit more than 5 seconds on this. What equation or equations, sometimes it's not just one, sometimes it is, sometimes you gotta use a couple, relates energy, capacitance, and voltage? See if y'all can find it. So if we look at our formula sheet, which again, at this point you all kind of always have access to, energy, capacitance, and voltage, you will not find it on here. You will not find one equation that relates energy, capacitance, and voltage. However, if you look back to the slides, that's because it is in the slides. So when we go back to that whole energy equation, let's see, where was that at? Boom. You can do the little bit of algebra to the other two versions. You don't want to do the algebra? Write these down on your 5x8 note card somewhere. So which one has energy, capacitance, and voltage? It's the second one. There it is. So U equals 1/2, I believe, CV squared. I'm not going to risk it. Yep, CV squared. And at this point, fairly straightforward, plug and chug. U is 36, C is 5e to the minus 6, and we don't know the voltage. So we'll divide by 5e to the minus 6 to cancel that. And then we will square root it to get the final answer. Okay, but I'm not gonna, that's a little bit too messy. So, V squared equals whatever that is. (7.2 e to the 6) square root to cancel that out, and that will equal a number. And yeah, as we mentioned, this is a very high voltage, 2,683.28 volts. This is the voltage that is applied. This is both the voltage that is applied to charge it and also the voltage the capacitor will have. Did I mess up somewhere? Oh, thank you. All right, so that should be 72. Yeah, good catch. So it'll even be bigger. All right, so 36 will double that. Ugh. I'll clean this up. Thank you for catching that. The good news is, very unlikely I'd give you an answer where I'd forget, like, so if this was the test, you probably wouldn't see this as an answer. So that's a good sign. I do put questions on the, like, answers on the test that if you use the wrong equation. So you best believe if there was an equation where I said find the energy stored in a capacitor, remember this is the equation, 1/2 QV, I can guarantee you one of the answers will be if you plug just Q times V, because there was an equation. The reason for that is because there is that equation, Q times V, and I want to see if people remember to use the right equation. So in that case, the half would end up throwing you off, but in this case, I'm not that malicious that I'm trying to find all the algebra mistakes. The other equations I'll give you all is if you're using the wrong, like when you're doing the test, the options will basically be if you use the wrong equation, that's what's going to catch you. Or one of my favorite ones to do is when we're talking about electric field, it's got the squared on the bottom, if you forgot to square the distance. Because again, if you forget to square the distance, you found voltage, not electric field, which again is a different equation. So that one is one that keep your eyes out for. Okay, so that was a bunch of words. I'm just going to do that 1/2 5e6 times 2. So we get 1.44 E7, square root that, and then we'll get our right answer. Yeah, 3,000. Bigger number, even bigger. So this is the voltage necessary to charge a capacitor. This is also the voltage the capacitor will have before it hits you, and this is necessary to pump current through your body. We're going to learn why next week, that you need a lot of voltage to run current through a body because of high resistance. We'll learn about resistance today. Okay, it says find the amount of stored charge at this point. Super easy. The last step is super easy. C equals Q over V is the other equation we're going to use. We have C, we have V. Just solve for Q. So that's the second equation we're going to use. The one that now that we have voltage, we can use that. So I'll go ahead and just copy all this to the other page that I already have prepared. Boom. So the next one also wants us to find Q. And so I will chuck that here, C equals Q over V. So C equals Q over V, plug in the numbers. So C is 5e to the minus 6 equals Q divided by 3,794.73. Why not put the second decimal place? It costs us nothing. Q equals those two numbers multiplied together, which equals something. So fairly straightforward problem. This is classic plug and chug. These problems should be freebies on the quiz, because there's not really anything fancy we're doing here. You really don't need, literally all you need to be able to do is identify the givens, identify the missing, find the equation that relates them, plug and chug. That's as easy as a physics problem can get. Now, we look at our answer and say, does it make sense? 1 coulomb is a lot of charge. So this answer may not seem like much. This is a lot of charge. Hence why it does such a good job. This is a lot of charge. Anywhere, a little bit of charge is like microcoulombs, 10 to the minus 6. That's a more normal amount of charge. 0.019 coulombs, that's a lot. That's a lot. Related to that, a 1 farad capacitor is a strong capacitor. That can store a lot of charge. Easy way, 1 farad capacitor can store 1 coulomb just with 1 volt. If you do the math, C equals Q over V. If you apply 1 volt, you get 1 coulomb. 1 farad capacitors are big. Most capacitors you'll see will be microfarads if you somehow interact with capacitors in your day-to-day life. It's always good to have a sense of scale. Is it reasonable? Yeah. Coulomb. Yeah. So this is also, the more variables I give you all, the more chance you have to mix up units and variables. C is the variable for capacitance. C is the unit for charge. So make certain you're careful. Hey, you think you're going to forget them? Put them on your 5x8 note card. It sounds silly, but I don't need you all to memorize anything in this class. Anything you think you need to memorize, that's what the note card's there for. What you may feel like that information may be that you are afraid of forgetting, that's what the note card's for you. So C is the variable for capacitance, C is the unit for coulomb. The unit for charge, which is coulombs. All right. Cool. All right. How much surface area is necessary to make a capacitor with a capacitance of 1 farad, assuming we have a gap of 10 micrometers and are able to maintain a vacuum in the space between the plates? What if instead we put a material in it with a dielectric constant of 5? This problem is fantastic for showing you that 1 farad is a big capacitor. Like, that's a lot, that's a strong capacitor. That can hold a lot of charge. So our givens here, capacitance is 1 farad. This gap is the distance. This gap is the distance between the plates. So 10 micrometers, that's going to be 10 e to the minus 6 meters. And I'm not going to put that dielectric until we use it. So for now, I'm not going to put it, but we will end up writing that down as a given for the second part. But for now, I don't want us to write it down just because I don't want us to think we're going to use it in the first part. In the beginning, we have a vacuum, meaning no dielectric. We are finding the area. And this is where I'll pause and say, see if you can find the equation that relates capacitance, area, and distance. That's what most of your time will be spent doing during the test, is finding the right equation. So capacitance, distance, and area. Great news, y'all. This one is on your formula sheet. Again, pretty much any equation you need is. The only ones that weren't were those different variations of the formula. So you can derive, when I said all those energy ones weren't on here, you can derive every single one of them by just doing what I did in class today, doing a little bit of algebra. So even if you don't have it on your note card, you can kind of figure it out through the problem if you just take your time. But this one's on here. And it is located right there. C equals epsilon naught A over D. If you're like, man, what's epsilon naught? 8.854. What are we doing? E to the minus. That feels off. All right, now I'm going to fact check myself. It's called the permeativity of free space. I'm sure I spelled that wrong. Yeah, okay, great catch on me. That should be e to the minus 12. So I'll update that in the thing. All right, so C equals epsilon naught A over D. Just plug and chug. 1 equals, now epsilon naught we just said was 8.854 e to the minus 12. So 8.854 e to the minus 12 times A divided by the distance, 10e minus 6. Now again, with you all, I write in the numbers and then do the algebra. You can also do the algebra before the numbers are in. Do whatever you're more comfortable with. If this is an engineering class, I would do it with the variables. With you all, I'm going to do it with the numbers because it's just a little bit easier to follow. Before you do any algebra, before you move things around, it's helpful to simplify what you can. So in this case, I can do 8.854 e to the minus 12 divided by 10 to the 6. Oh, and I'll also mention this now, because this is a question I do get from time to time. These are the same thing. Epsilon not being in the front is just the same thing as being on the top. Those are the exact same equation. Good for me to clarify that, because some people, it is sometimes like, why is it in front instead of on top? We just like to put constants in front. That's why. You'll see that in the equations. If it's a constant, we like to kind of pull it to the front. That's just a notation. But these are the same thing. Anyway, so 8.854 e to the minus 12 divided by 10 e to the minus 6. So I get 1 equals 8.854 e to the minus 7 times A. And now the game, the algebra is a little bit easier to see. We're going to divide. Divide that over, and life will be good. That'll make that go away. And my area ends up being... And look how wild this answer. Yeah, there's something off here.
Plug in your calculator e to the minus 7 or e to the minus 12.
Thank you. It's even more ridiculous. Thank you. Weird how I did. Oh, no. 7's good. Because I divided by 10e minus 6, and it changed it. Yeah. I was like, that's weird. Yeah. So it is e minus 7. Yeah, because we divided by that 10e minus 6. Yep. Thank you for checking, though. The area is 1.129 times 10 to the 6 meters squared. This is huge, y'all. Let's write this out in not scientific notation, because sometimes scientific notation can get hard to see what the number is. 1,129,000 meters squared. That's a lot of area. That's a lot. Like, you're not going to fit that in a little thing this big. Now, there is 1 farad capacitors, and they are about this big. So what do? You got some options. One, increase the distance. Pick a material that's thinner than that. Make the gap even smaller than that. The second option, put a dielectric in it. Remember, if we like the pure water situation, that made it 80 times. That would make it 80. Well, we'll see here. How much surface area is necessary if we had a dielectric of constant 5? Let's see what happens. So it's going to be the exact same problem. So all the givens are going to be the same. Let's go ahead and copy all this over. So if I repeat this entire calculation, but with a dielectric constant, so part B, in part B I know kappa, that's the dielectric constant, is 5. It has no units to it, which is kind of weird. Has no units to it. Our equation is C equals kappa epsilon naught A over D. Same equation, just we chuck kappa in front. So we plug in the exact same numbers. 1 equals 5 times 8.854 e to the minus 12 times the area divided by the distance. The cool thing is, I could do all the math here, but what it ends up being is it becomes the area is 5 times smaller. You can prove that for yourself by plugging all this in, but I'm going to save myself a tiny bit of time. Feel free to work through this. The area, if you do the math here, is just 1/5 the area before it. Because there's a 5, everything is the same, there's just a 5, I'm just dividing by 5 now. All the other numbers are the same, I'm also just dividing by 5. So take your area from the last part, divide it by 5, and we get 2.25 e to the 5 meters squared. So, if I have a dielectric constant of 100, I need 1/100th the area. So that's the benefit of the dielectric constant. Makes it so we can make these things smaller. Now, all these capacitors, they're generally one of the bigger circuits in your thing, because at the end of the day, you have to have some area. You've got to have place for this charge to build. So that's why in circuits, these things tend to be some of the bigger, and you can actually see them regardless of the circuit. They're always kind of visible. Whereas when we talk about wires, some of those are so small you can't even see the wires. When we talk about resistors, some of those are so small you can't see them. Anyway. But yeah, it's a good problem to show you that 1 farad capacitor, it's not simple to make, necessarily. Okay, the last thing we're going to cover, it's not much. We're going to get into, so capacitance, great. It's a thing that stores charge. Now we're going to start getting into circuits a bit. And one of the key parts of circuits is they run through wires. And these wires have something called resistance. And so that's what we're going to be talking about. Resistance is exactly what it sounds like. It's resisting the flow of electricity. It's nice, right? These words. Now, before we can talk about resistance, different materials have different resistivities, aka different materials resist electrons more or less. Electricity flows better through some things than others. Some things than others. Example, wood is a very bad conductor. You can almost think about this. How good of a conductor is it? The smaller the resistivity, the less it's resisting it, the better of a conductor it is. The higher the resistivity, the more that material resists it, the worse conductor it is. So we can see here silver, copper, gold, basic metals. Shock and awe, they conduct electricity well. We're all very surprised by that, I know. Now what's kind of nifty here, silver is a better conductor of electricity than copper, but silver is more expensive, so, we don't use silver for our wires. Fun fact, your all's phones do have gold wires in them. It is not because they are better conductors, it is because gold is... The reason gold is so valuable is it doesn't react with other things. It doesn't rust. The reason everyone throughout the history of time has enjoyed gold is it doesn't rust. Not many people value, like iron. A piece of iron left out in the rain is going to get turned into rust and disappear at some point. You leave a piece of gold out, it stays nice and shiny, and people are like, oh, so pretty. A piece of copper can look, a piece of iron, you can shine that up and it'll look real pretty, but a piece of copper shined up will look real pretty, but it will rust. And for your all's phones and stuff like that, there's some key elements in it that, we don't. Actually, most of the wires in your phone are gold because they don't rust. They don't degrade over time, which really matters when you're talking about wires that are just like, you can't see them with your eyeballs. So, fun fact, gold is used in a lot of circuitry, but it's actually a worse conductor than copper, but it doesn't rust. So, fun facts. Okay, so resistivity, it does change with temperature. I'm going to straight up tell you, don't stress this too much. We'll talk about it. I will not test you on its dependence upon temperature. It's interesting, but it doesn't really give you too much. Let's see. Do I ask a question about this, though? Let's see before I spoil any answers. Do I even want to bother with this? No. I'm going to open this and I'm going to solve it with you all. And then we'll actually talk about why. Oh, great. Well, let's talk about why first. All right. So we're going to get into the flow of electrons. Resistivity is how easily electrons flow through it. So, here's a wire. Every material, everything that's made of stuff, everything with mass has electrons in it. Everything. I guess you could take them all out if you tried hard enough. But in general, everything's got electrons flowing around it. Metals, if you remember from your chemistry class, are special in that these electrons are free to float around. They're free to move around. So insulators, they're trapped. So if you have an insulator, the electrons are kind of trapped. They can't escape. They're stuck to the atom. But when we talk about, so these are kind of my proton, these are my nucleuses, whatever, obviously they got more than that. The electrons are free to float. That's what makes a conductor special. That's what's so special about a conductor. Is they got these electrons just kind of, floating around, moving around throughout the thing. Now, when I put a voltage, we've talked about, they're going to go from the high voltage to the low voltage. Sorry, the other way around. If I have 0 volts on this end and 12 volts on this end, these electrons are going to want to start zipping to the left. All these electrons are going to want to start zipping left to right. Sorry, right to left. They're going to go to the higher voltage. Okay, why does temperature matter? This is a lot of buildup. You have to think about what is temperature. Like on a fundamental level, when something gets hot, what is actually happening? The molecules are literally vibrating more. That's all temperature is. Temperature on an atomic scale is things wiggle around more. The more they're wiggling, the hotter it is. So, if the temperature increases, these things are wiggling around faster, and you could think about it this way. It's easier to move through a crowd where the people aren't moving versus a crowd where everyone's hustling and bustling all over the place. And so as temperature goes up, they wiggle more, and it's more likely it's going to bump into something. So, as temperature goes up, conductors actually get less conductive. And at some point, I guess they can melt, but that's beside the point. So that's why your all's computers and stuff like that, if they get too hot, it runs into problems. It likes to be a little warm, but not too hot. Okay, this problem again, I'm going to work through so you can see. So as temperature goes up, wiggle around more, the electrons literally just bounce off more things. Just like you walking through a crowd where everyone's running all over the place. It's chaos. Okay. So what temperature change is required to double gold's room temperature resistivity? I'm going to kind of work through this with you. So resistivity is given by this equation. Resistivity equals its resistivity at room temperature. That's this rho naught times 1 plus alpha. Alpha is based on the material. There it is. Times the change in temperature. Okay? So, if I want to double the resistivity at room temperature, that means, what is my resistivity at room temperature? This is resistivity at room temperature. So if I want to double the resistivity, I want double that. So that's what I want. So if we just plug that into our equation, I want to double it. Before I even put in any, let's just even replace this with change in temperature. Well, both sides have that. Fun fact, you didn't even need it for this problem. If I want to double it, I just double it. I doubled it on the left side. So I get 2 equals 1 plus, let's start putting in numbers. And now it's just a math problem. Subtract the 1 over. So I get 1 equals 0.0034 delta t. And then all I need to do is divide 1 by that. And I should spit out the right answer, fingers crossed. I feel like this question's had... Yep, good job, man. There you go. So, okay, what's the point of doing this problem? One, it lets us see this equation. Again, I would tell you I'm not going to test you on this, but it is important for you all to know that as wires get hot, electricity doesn't flow through them as well. That's an important concept to understand because things get hot, things get cold. That's important to kind of know what the consequence when it comes to circuits is. This problem is kind of nifty because it shows you to double it. You got to increase the temperature a lot. 294 degrees, increasing the temperature by 294 degrees. That's hard to do. We're nowhere near the melting point, so that's not a concern. But that's real hot. I mean, the boiling point of water is 100 degrees Celsius. We're way past that. So, it's not, this process for the most part doesn't matter. Like if you take something out in 100 degrees Fahrenheit outside versus it being inside, it's not going to change much. So this effect only happens when you really get quite toasty or when you're really sensitive to changes. Maybe you have a device that really matters what your resistance is. But again, I do want you all to know that increasing temperature makes electricity harder to flow. That's kind of the major takeaway from this. Colder temperatures, easier to flow. Okay. This is purely based in the material. Different, just like I showed you all here, the resistivity purely depends upon the material and temperature. Okay, so purely depends upon the material. So now we're going to introduce something called resistance. And this is kind of analogous to capacitance in that it is purely based on what the thing is made of and the shape of it. So remember capacitance? The capacitance of something purely depended upon was there a dielectric and basically the size of these plates. Resistance, same thing. Purely depends upon what is the wire made of, what is my cross-sectional area, and how long is my wire. Okay? Easy analogy. A road. Let's think about a road. What determines, so resistance is how much does a wire resist the flow of electrons? How easy is it for electrons to go through them? So let's replace electrons with cars and our wire with the road. If I make my road larger, I go from a small road to a big road. I go from a 1-lane highway to a 4-lane highway. It's easier to drive. The more lanes there are, the bigger the area, that cross-sectional area, the more room there is, the lower the resistance. Area's on the bottom. The bigger the area, as area goes up, resistance goes down because it's on the bottom. Just like a highway. the more lanes there are, the easier it is to drive. Fantastic. Let's look at length. The longer your road is, kind of the longer it's going to take you to travel down that thing. Short road doesn't take you that long. Long road takes you a while. And in the case of resistance, the long road, it's literally more think of a race. If someone has to drive their car a mile versus 10 miles, the person that's driving 1 mile gets there quicker, easier. So the longer the wire, literally the more atoms they have to get through. So as length goes up, my resistance goes up. Makes sense? Longer wire, more I got to get through. Harder it is to go through that thing. So more lanes, lower the resistance. Longer the wire, higher the resistance. And the last one is resistivity. Think of it like a road. It's easier to drive on a nice paved road than it is a bumpy, dirty path. Resistivity is based on the material. So resistivity is based purely upon what is it made of? Copper, gold, wood. No one's making wires out of wood, but whatever it may be. Resistivity here is purely based on the material. So resistivity is what it's made of. It is made of. Resistivity is based on that. So, if I drive on a nice smooth highway, I can go faster. If I'm driving on a dirt road, hopefully you're going slower. So, as resistivity goes down, resistance goes up. As resistivity goes down, resistance goes down. Because remember, resistivity is how hard it is to travel through it. Smaller resistivity, the better. Smaller the resistivity, the better. Okay? So, that's what this equation says. And it's just purely based on what the wire... If I give you a wire plugged into nothing, we can calculate the resistance of it. It does not matter what we're plugged into. It does not matter what's connected. Just like the capacitor. The capacitor does not matter what circuit you're connected to. It's based on the area, the distance, and whether it's a dielectric. Okay? Alright. So, at this point, we just kind of got a few things to kind of practice this, and that'll be it. Okay. Here's the derivation. Don't worry about it. Again, if this is engineering or you're physics majors, it comes from something. It wasn't just made up. Conceptually, I explained where it came from. That's good enough for us. This requires Maxwell's equation, and there it's gone. All right. Fantastic. Oh my gosh, we've been on the last clicker question for 8.5 minutes. Hopefully everyone answered it. All right, and I'll go back and pick the right answer for it. If I double the length and half the diameter, what is the value of its new resistance? And because I like y'all so much, here's the equation for resistance. If I double the length and half the diameter of the wire, we're going to assume that every wire we interact with has a circular cross section. That's my hint to you all. There is no square-shaped wires out there because they'd be very hard to make. Circular wires are just functionally easier to make. We'll do like a minute 40 on this. We'll go for like 30 more seconds. 40 more seconds, sure. So we'll go to 150. All right, in 5, 4, 3, 2, 1. All right, so if I double the length and half the diameter, here's where you had to realize something. The area, remember this is a circular cross section. The area of a circle is pi r squared, which is pi times diameter over 2 squared. Now, honestly, if you half the diameter, you're halving the radius. That's going to happen, but just to make it so, if we plug this in, if we plug in what happens here, we are doubling the length. You know what? I'll just write it with everything original. R naught. Length over pi times d over 2 squared. So R1, my new one, is going to be resistivity is the same material. Double the length. And my diameter halved. This is going to go a little tight in here. So what ends up happening, if I give myself more room to write this out, so R1 equals rho 2L over pi 1/4 d over 2 squared. Because that diameter gets squared, 1/2 squared, I just pulled that out. 1/2 squared is 1/4. Now we're going to pull all that to the front. We're going to pull the 2 to the front. We're going to pull 1 over 1/4 to the front. And then we have L over pi d over 2 squared. This chunk here is my original resistance. So this and this are the same. So if we just do a little bit of math, 1 divided by 1/4, that's going to be 8 R naught. Okay. So this one, it's kind of like it's a mean one in some ways. It's a little mean because you had to realize that the area, but I still like this one. This is kind of the worst type of this one I could ask, where you had to recognize that area was based on that. But I like this because I don't want us to get used to the things I give you will automatically just be in one equation. In this case, we had to visit, diameter is not area. How do I go from diameter to area? Area equals pi diameter over 2 squared. Okay, and it ends up being this. And then it's squared, so whatever I do to diameter, whatever I do the radius also gets squared. So this is a great one to look back on after a day or two and see if you can get the answer without having the answer right in front of you. Without having the answer right in front of you. That kind of ruins all the goodness. All right. So, because I was so mean in the last one, I'm going to give you all a very major hint on this one. Same problem. If I double the length and half the radius, what's its new resistance? The last problem was halving the diameter. I'm going to tell you all, if you half the diameter, you're halving the radius. So in this problem, everything is the same. I replaced diameter with radius. If you half the diameter, you are halving the radius. So we'll only go to, we'll go to 110, give you all 30 seconds for this. And you kind of realize that that's the reason for asking this is, again, it's good to know the relationships between radius and distance, and we love circles in physics. Big fans. All right. So we got 10 more seconds. All right. And 5, 4, 3, 2, 1. The answer is the exact same as the last one because it's the exact same problem. Halving the diameter is halving the radius. This is the exact problem as the last one. They're the exact same thing. Easy example this. If my diameter was 4, halving the diameter is 2. In this case, my radius was 2. In this case, my radius is 1. Halving that diameter is the same as halving the radius, or the same thing. Okay? feel free to look at that, check that out. All right, last thing I want to leave you all with. Here's what a resistor actually looks like. You do not need to know what's on. This is actually how you read them. No one writes little numbers on the resistors. They use these little color coding thing. You don't know how to read. You don't need to know how to read them, but it's kind of each of these numbers correspond. Each of these colors corresponds to a number, and you do kind of some mathy things. Fun to look at if you're curious. You will never see a resistor with a number written on it because they're so small. You can't read the numbers, but you can read the colors. And then next class, I will solve these problems. Not this one because it's not worth the time. This one, yes. And we'll get into circuits. And it'll be, again, next week's stuff will be fairly smooth, simple. Hopefully this stuff didn't feel too bad. Whatever extra time you have, polish up your vector stuff, your electric fields, that kind of stuff. I'll see you all Tuesday. Good luck to you. Have fun.